So welcome to the second lecture, the CS580 computer graphics. And today we are going to discuss the basics about the OpenGL based the graphics pipeline. So last time, I gave some kind of the quick introduction about the course, and then I mentioned that we're gonna have the three major parts in the course. So first, we're gonna recap some of the basics about the computer graphics the pipeline, and then we're gonna discuss more like the advanced the rendering the techniques, and then we're gonna also discuss some kind of the basic ideas about the neural rendering the techniques. So for today and also for the next week, we're gonna have some kind of the discussions about the basics of the graphics the pipeline, and then we're going to move on to the ray tracing based some techniques. And also please note that we are not going to have the lecture next Wednesday. So we're going to have today's lecture and also the lecture in the next the Monday, and then we're going to have a break for the next Wednesday, and then we're going to resume after that. So please also check out all the schedule in our the course webpage. So yeah, let's get into the basics about the graphics. So basically, like what we do in the computer graphics, the pipeline is basically kind of like simulating the situation that we are basically shooting the film. So when you think about like shooting the film, there can be some kind of the some essential the components that we can think about in terms of like how we're gonna basically sort of like mathematically like represent all the things. So there can be some multiple things. So basically we will be able to basically represent some kind of the 3D objects in the scene, and with some kind of the representations about their geometry and also the appearance as well. So these are like, we are having some kind of the objects and the actors, whatever, some kind of the buildings, whatever kind of things in our this 3D scene. And once we have these kind of some 3D objects, we also should be able to basically make some kind of the animations, which is kind of like giving some directions. For example, like to the actors in terms of that, they can make some kind of the actions in the 3D space. And for that, we should be able to basically somehow, represent the transformations in the 3D space and also some kind of the interpolations as well. So once we have these kind of the objects and they're the animations, then now we should be able to basically capture all the things into the image. So that's basically the things that we should be able to somehow model the camera. So basically how we're going to basically capture all these kind of like 3D things into the 2D image. So for that, we should be able to basically see basically how the camera basically works in terms of capturing all the things. And also for that, we also should be able to basically have some kind of the models of the lighting as well. So in terms of that, we are simulating the light transportation in this space in terms of that, like all the lights are basically coming into the lens of the camera so that we can make some kind of images. So what we basically discussed in the introduction to the course in the CS380 is basically discussing all the kind of things, like very basic things about like all the things about the objects and the animation, the light and the camera, basically how we're gonna represent all the things in with some basically the numbers. So those are basically the basic ideas that we are discussing in this CS380. And in this advanced course, we're gonna focus more on the basically appearance and the lighting and the camera in terms of like how we can do some more like the precise some kind of optic simulation in terms of like we are making some more realistic images. So that's basically what we are going to discuss over the semester in this course. And in terms of like capturing all these 3D scenes into the 2D images, actually there are two main kind of the pipelines that we have discussed so far in the computer graphics the history. So until the like 1980, what people mostly focus on was basically this like rasterization based the framework, which is still being used in the many graphics application. So especially for many kind of the pipeline, which is based on the OpenGL and also many other kind of things, basically the basic the rendering the framework is the rasterization based the framework, which is basically projecting all these 3D things into the 2D plane and do some kind of processing in the image space. And this is what we are going to briefly review for today. And the other basically the rendering the framework is the ray tracing based the system, which is not projecting 3D things directly into the 2D plane, but actually shooting the ray from the 2D plane into the 3D space in terms of like we are sort of like following the reverse way of the lights, and basically start from the images and see how the lights basically reaches some kind of the light source with some kind of the interactions with some kind of the 3D objects. So these two might be basically some major kind of rendering the frameworks that we can see in many kind of the graphics the applications. And the focus of the CS380 was basically discussing the rasterization, the pipeline. And then in the CS580, we're gonna discuss more about this ray tracing based the frameworks. So what we are going to discuss more details in the rest of the lectures in the entire this semester will be basically about this like ray tracing based the techniques. But for today, we are going to briefly review the basic ideas about the rasterization. So what we are going to do for today is basically briefly review what we have discussed in the CS380, especially for the students who did not take this course or who may not remember what we have discussed this basically course. So let's briefly review the OpenGL-based the graphics pipeline. So we are basically starting from some kind of the raw geometry, as you can see on the left-hand side. And then we are basically having some multiple the components that we are processing this kind of the geometry information. So actually, we are not only having the geometry information, we also have some kind of the appearance information like the texture and the lighting, all the things, some material information as well. And we are going to discuss this kind of like material and the lighting information in the rest of the course. And so we are going to skip those parts. So we're gonna focus more on basically how we're gonna process the geometry information for today's lecture. So when you have some geometry information, there are some kind of the multiple the components. We are having some the vertex processor and also the rasterizer and also the fragment the processor and merging all these outputs in terms of that we are getting the final images. So as you can see, those are some kind of the components that some of the components are something that actually we need to implement. So if you see the OpenGL framework, in the very classical the framework in the OpenGL like 1.0, like all these kind of the components are basically implemented. It's kind of like hardware implemented, so kind of the components. But in some kind of the modern the OpenGL based kind of the framework from the like 2.0, actually you can implement the vertex processor and the fragment the processor as you want. So these two are basically kind of the programmable the components, while the rasterizer and the other components are basically some sort of the fixed components which is already implemented in the hardware. So which means that you can implement the vertex processor and the fragment processor as you want based on the shader language. So we have the vertex, the shader language, and for the shader language for the fragment, the processing as well. But there are some kind of the typical ways to basically implement these two components. So especially for today, we are going to focus on basically how we need to basically implement this vertex processor. And then we're going to also see how this like rasterize also works in the OpenGL pipeline. So let's first see basically how we're gonna represent the raw geometry first. So there can be actually the multiple ways that we are representing the raw, some kind of the 3D geometry. But the most conventional way to represent some kind of the 3D geometry might be using some triangle mesh. So basically triangle mesh is basically nothing but basically having this kind of some sort of the net, like some kind of the sort of the graph structure that we are having some kind of the collections of the 3D vertices and then connecting them in terms of that we are forming some kind of the lots of the some sort of the triangles in the 3D space. So it does not need to be exactly some triangle mesh. It can be any kind of the polygon mesh, but the triangle mesh is the kind of simplest form in terms of like representing the surfaces in the 3D space in a kind of the compact way. So typically for the triangle mesh, we're going to have some kind of a set of the vertices, which is basically the 3D points in the space. And then we are connecting them with some kind of, so basically forming some kind of the faces, which are basically the triangles by just taking 3 vertices. And for each of the vertex, we're going to have some sort of the extra information that can be the surface normal information, or some color information, or some texture coordinates, or some many other things. So let's think about that we are basically having this kind of the geometry information. And then we're going to have the vertex processor, which is also having some kind of the multiple the small components as well. So these kind of the components that you can see in this kind of the pipeline are actually kind of like having so many kind of details. Actually, there are some kind of even multiple lectures to discuss all the details for each of the components. But we're gonna basically go very quickly for each of the things and see what we need to do. So in the model view, the transform, so this is basically the process that we are basically placing some 3D objects in the scene. So when you think about like making some kind of some 3D virtual scene, we're gonna have some kind of the 3D objects which are basically defined based on the local coordinates. So as you can see, we are having this box in the 3D space, which is now defined with its own the 3D local coordinates. And we want to place this kind of the box in the 3D the space in a way that we can basically composite the multiple the objects in the scene, which will be basically the kind of the process that we are converting the local coordinates into the global coordinates. So we are basically defining some kind of 3D objects into the local the coordinates, but now we are representing the same object based on the global the coordinates, which is defined based on the camera pose. So precisely like what we can say here is that see, we are having some another coordinates, which is actually called the world coordinates. And we can think that like given this kind of the world coordinates, we are having the object coordinates and also the camera coordinates as well. So what we want to do is that we are placing all these 3D objects in the world coordinates and then also transforming the entire things in the world coordinates into the camera coordinates in terms of that we are basically seeing how those kind of the 3D objects will be seen from the given the camera. And this kind of the two-way of the transformation from the object coordinate to the world coordinates and the world coordinate to the camera coordinates, these two processes actually can be like just like called as kind of the model view the transformation. So that's basically what we typically do in the graphics the pipeline. And also for those kind of the transformation, actually there can be some multiple the types of the transformations, and we're gonna consider the affine transformations. But here the question is that what's the affine transformation? So actually there are lots of the types of the transformations, right? So we can actually there can be some multiple ways that we are basically classifying all these kind of the transformations. So we can think about the ridge transformation, Euclidean transformation, and also the similarity transformation and affine transformations and the product transformations. So can you classify those kind of the classifications and what are the kind of the differences of like these transformations? So let's think about the differences of those things and please type your answer in our Slack channel. So you can find the lecture 2 channel in the Slack the workspace. And let's think about the differences of those transformations and please type your the answer about those the ways that how we distinguish those transformations. So I will give you 2 minutes to think about the differences of these transformations. So your answers for the quizzes will be counted for the participation score. So please post the answer, and your answer does not need to be correct. So let's just think about this and just like type the answer. Yeah, maybe you can go one by one. So when we typically talk about like ridge transformations, those are basically the transformation that we can see for some kind of the ridge body, the objects. So let's think about the case that we are basically throwing some kind of the objects in the scene. Then the transformation that we're gonna see would be basically some kind of the some translation and also the rotation as well, right? Like just like moving some kind of the objects in the scene, then those might be basically some translation and the rotation that we can typically see in many kind of some robotics kind of situation, moving some kind of objects, whatever, those kind of things. And when you talk about the Euclidean transformation, that basically includes everything in the ridge transformation and plus the reflection as well. So those are basically the cases that we are having the translation, rotation, the reflection. And when you also talk about the similarity transformation, this is typically the case that we are saying is kind of like adding the uniform scaling. So if we have the translation, rotation, the reflection, and also the uniform scaling, these are the similarity transformations. Affine transformations are basically some broader the class of the transformations that we are also adding some kind of the non-uniform scaling and then shearing as well. So shearing is kind of like shifting some parts of the objects while basically preserving the parallelism, as you can see here in this image. Yeah. So those are basically the cases of the affine transformation, and the project transformation is basically including everything, including the projection as well. So those are basically some kind of the classes of the transformations. And for many kind of the some graphics and also the vision, the applications, you might need to basically see what's the kind of the exact the definitions of the transformations. So actually, there are also lots of the details that we can discuss about this kind of the transformations. Basically, there can be some kind of the properties that will be preserved or that will not be, they may not be preserved for some types of the transformations. So there are some kind of details, but we are not gonna discuss all the things. But basically, the thing is that, so here the question is how we can represent this kind of the affine transformations with some kind of the numbers, some in kind of the mathematical the way, and the kind of the typical way that we are representing this kind of the affine transformations is to basically using some kind of the 4x4 matrix and also the homogeneous coordinates. So we are basically extending the 3D the coordinate system with the XYZ by adding one number with one here. Then now all the kind of the affine transformations can be represented with the 4x4 matrix while having the last row to be basically 0, 0, 1, 0, 0, 0, 1, right? So when you have this kind of the 12 numbers, then now we can represent any kind of the affine transformation, and especially the transformations that can be represented with the first 3x3 matrix here is also called the linear transformation. So linear transformation is basically affine transformation minus translation. Yeah, so all the transformations that can be represented with the 3 by 3 matrix here, and then we are adding the translation here as well. Right? So those are basically all types of the transformation that we're gonna represent in our the kind of the model view transformations. So basically the model transformation is basically represented with a single, can be represented with a single the 4 by 4 matrix, which comprises the linear transformation and the translation like this. And in the next lecture, we're gonna get into slightly more details about the 3D rotation. But before that, let's also briefly think about some kind of the 3D rotation. So let's check whether you have some kind of the basic understanding about the 3D rotation. So let's think about the Euler angle representation. So even you don't need to know what's the meaning of the Euler angle representation. So let's just like ignore this. But we are going to have a 3D rotation, which is basically combining these 3 rotations. The first rotation is basically rotating along the x-axis with the angle alpha, and then we are rotating along the y-axis with the angle d beta, and then we are also applying the rotation along the z-axis with the angle d gamma. So when you have this kind of the sequence of the 3D rotations rotating along the x-axis and then y-axis and then z-axis, how this kind of rotation can be represented with the 4 by 4 matrix. So let's think about this. And please type in your the message. So you can actually just like write down those things into the paper and just take a photo and post the photo in the Slack. So this is the second question. And also you don't need to basically make a single 4 by 4 matrix. Actually, as you can see, this will be represented as kind of the multiplication of the 4 by 4 matrices. So you can just like put the multiplication of the matrices without exactly calculating all the multiplications. So let's just type this. So yeah, basically we are multiplying the coordinates on the right-hand side, which means that if we want to rotate from the x-axis and the y-axis and the z-axis, then we're gonna multiply the matrices in this order, right? From the rotation along the x-axis and the rotation along the y-axis and the rotation along the z-axis. Right? So those are basically what we are going to do. So those are kind of some very basic things. If you also find some kind of typos in my slide, please let me know. But yeah, so those are kind of the very basics about the some transformations in the computer graphics. And for many kind of the some graphics 3 applications, you might be able to basically handle these kind of transformations that you want. So so yeah, we are not gonna basically discuss such kind of details, but just giving this quiz just to let you know that we are assuming that you have those kind of the background for this course. Cool. So yeah, these are basically some ways that we also representing some kind of the affine transformations. And especially for this 3D rotation, there are some kind of the other the ways around basically to represent all the things. So there can be some other ways like the, so we're gonna basically discuss some kind of the quaternion in the next lecture. So which is also another way to represent some kind of 3D rotations. Cool. So, but here the basic idea is that we are representing all this kind of the some model view, the transformation into a using some kind of the 4x4 matrix, which is basically the case that we are transforming the object coordinates into the camera coordinates, typically through the world coordinates as well, but we are basically skipping that sort of the details. Then the next step might be is that now we want to basically project all these kind of the 3D objects in the scene into the 2D plane. So that's basically the things that we are doing with the camera projection, which is now converting the camera coordinates in the system into the clip coordinates. So this is kind of conversion from the camera coordinate system and clip coordinates. And this is like all about basically the projection. So actually, there can be some kind of the more precise way to basically model the camera, the capturing. But let's think about the simplest case, which is basically having the pinhole, the camera model. So this is the case that we are assuming that we are basically having some very tiny hole in the box where basically we are projecting all the kind of the things in the 3D into the 2D plane like this. So let's think about how we can model this into some kind of some sort of the mathematical form. In the OpenGL pipeline, so we are assuming that now we are seeing the 3D scene along the minus z direction. That makes sense. So this is kind of the conceptual image for the 2D case that we are only having the y-axis and the z-axis. And here the idea is that the z-axis is the direction to the viewer. And we are basically seeing this 3D scene along the minus z-axis, right? So there are some kind of the objects. Now we are having the arrow here here basically this the 2D space, but it can be kind of like something in the 3D space. So we are having this point in the 3D space that we are seeing, which is having the two coordinates like y and z. And let's assume that we want to basically see how this kind of the objects in the 2D or the 3D space is projected through the pinhole here at the origin into the image plane, which is defined that the z becomes the 1, z is equal to 1. So this is the image plane where we are projecting everything through the pinhole at the origin here, right? So this is the pinhole. Then where is this point P, which is having the y and the z coordinates projected into the image plane? So given this kind of the P here, which is having the y and the z coordinates, which will be projected in the image plane, which is also the plane at the z is equal to 1, what's basically the coordinates of the P prime here? This is easy question. So this is basically nothing but we are having the y and the z, and we want to make the same ratio with the y prime and the 1, right? Then what we can see is that y prime is nothing but y over z, right? Yeah. So that's the kind of thing. So we're gonna basically have the y prime, the p prime, which becomes like having these coordinates. So that basically means that the projection is basically the step that we are basically calculating this kind of the converted the coordinates from the given the y and the z. But the kind of the problem is that if we do this kind of projection, then we are basically having this kind of the upside down, the flipped image. So we want to flip again in terms of that we want to get the correct images like this. So let's think about the process that we are projecting into the z is equal to one plane and then flipping the image, right? Actually, this kind of the two steps, like projection to the z is equal to one plane and the flipping, is actually exactly the same as like we are just projecting to the z is equal to minus one plane. So what we can actually do is that instead of like doing these two steps, like projecting to this image plane and the flipping, we can consider like we are now just projecting into the z is equal to minus one plane. Then we get these coordinates, right? P double prime, which becomes the like minus y over the z and the minus one coordinates. So this is basically the kind of the coordinates that we want to see through the projection, which is the same as like we are projecting into this image plane, right? Then also this is kind of the things like how we should basically represent this kind of the projection, the operation. So basically what we want to do is that we want to have any kind of the 3D coordinates. Let's think about that now. We're having the x, y, z, 1. And we want to map this into, what is that? Like minus x over z and minus y over z and the minus 1 and the 1, right? Then here the question is that how can you also represent this kind of some mapping operation, this mapping operation? And the thing is that this mapping operation can be also represented as a single 4x4 matrix if we utilize the properties of the homogeneous coordinates. So the meaning of the homogeneous coordinates is not just like adding the one at the end, but we are also having this kind of property, which is basically that if you multiply any kind of the constant, this color, the value to the all the kind of the four the coordinates here, then we just treat them as kind of the same coordinates. So this is basically the basic idea about the homogeneous coordinate system. In terms of that, we are augmenting the 3D coordinates here by adding the one here, while basically also treating them like multiplying any number, the non-zero number, when the W is not zero, basically multiplying any kind of the non-zero number to all the four coordinates is basically making the same the point. So that is basically some kind of the augmentation of the 3D coordinates into the 4D space using the homogeneous coordinate system. So when you basically have this kind of the property, and when you want to map the x, y, z, 1 to some the coordinates of the minus x over z, minus y over z, and minus 1 and the 1, can you represent this mapping using some kind of a single 4x4 matrix? So this is the question of the projection. So let's think about a simple 4x4 matrix that can now map these points into these points. How can you make this kind of the 4x4 matrix? Well, a kind of the hint is that in the homogeneous system, now we can say that actually these are exactly the same as we have. So if you multiply minus c for all the points, then we get x, the y, and z, and the minus g, right? So actually it's the same that we are mapping x, y, z1 to the x, y, z minus z, right? And also one thing is that we can actually, have this like the matrix for this mapping without having any numbers here, X, Y, Z. So we can have just like all the constant numbers in the matrix. So which means that for any, X, Y, Z coordinates, we can just like multiply a constant, the value of the matrix in terms of having this mapping. Yeah, so as you're posting now, well, actually what we can simply see is that this is nothing but basically, for the X and the Y and the Z, we want to just get directly the same thing, like X, Y, Z here. The only thing is that for the coordinates that we are adding in the homogeneous coordinate system, we want to map the 1 to the minus Z, right? That what we need to do is that in the matrix, we can uh, yeah, make the matrix like this, 1, 1, 1, and having the minus 1 here, so that we can get the minus z, which will be divided by all the coordinates, then we get this kind of some projected coordinates. So here the thing is that this kind of the projection can also be represented with the single, the 4 by 4 matrix, and also with the homogeneous coordinate system. So which is good because everything can be just like represented with the single, the matrix, the matrix, the multiplication. And also the thing is that when you have this kind of the projected transformation, now we are no longer just having the 4 by 4 matrix with the 0, 0, 0, 1 in the last row. But if we start to have some kind of some other kind of the numbers in the last row, then now we can define some kind of the projection as we can see here. So this is also the basic idea, like making some kind of the some projections. But this is kind of the most, basically the simplest case that we are making some kind of projection. But what we typically do in the real the graphics the pipeline is that we are basically defining this kind of the viewing transform. So these you can think that we are having this kind of the image plane in this 3D space, and then we are shooting the ray into this 3D space, and these kind of are basically region that we are basically assuming that we are seeing in the 3D space. And then we actually, instead of like just projecting this view frustum into the 2D plane, actually we want to somehow map this kind of the view frustum into the some kind of the unit box, which is called the canonical the view the volume like this. So this is basically the volume which is having the unit scale from the -1 to the +1 for the all the x and the y and the z axis. So given that we are having this kind of the left side, the bound of the view frustum, and also the right hand side, the bound, and also the top and the bottom, and also the some kind of the some range of the along the z-axis from the near to the far, which is defining this kind of the view frustum in the 3D space. Actually, we want to define some kind of the some projective transformation, which is mapping this kind of the some truncated the some kind of the cone shape into this kind of the unit box here, which becomes the some projection of the matrix that we want to do in our some camera of the projection. So when you basically define this kind of the view frustum with the left right bound and the bottom top the bound, and also the far near. So the near is basically the z-axis, the end point of the one of the z-axis, the range, and also the far point here. So when you have this kind of the some range along the x and the y and the z-axis, which is defining the view frustum, we want to map this view frustum into this kind of unit box in terms of that we want to do some kind of the processing with this kind of the normalized some kind of the coordinates. So this is what we typically do with some kind of the projection. So a kind of the homework that I want to give you is to also think about the 4x4 the projection the matrix, which is mapping this kind of the view cluster defined with the range along the XYZ axis into this kind of the unit cube defined with the -1 to the +1 the range vertical axis. So think about this kind of the 4x4 matrix doing this kind of the projection from the view cluster into the some unit cube. Okay, so that can be the quiz in the next lecture. But then you might think that why do we need to basically map the view cluster into the unit cube? So instead of that, we could just like consider basically simply mapping everything into the 2D plane, right? So that's what we have seen in the previous slide. But instead of like just doing the projection into the 2D plane, why do we want to map everything into the some kind of the unit cube? So that is basically the process that we are not only projecting into some kind of the 2D plane, but actually we want to preserve some kind of the depth information. So here what we do is that we are not only getting the kind of the 2D coordinates in the projected plane, but we want to basically somehow keep some kind of the information along the z-axis, along this direction into the unit cube. So we are now having x, y, and also the z-axis, z coordinates in the normalized the coordinate system. And this information will be used in the depth test. So what we do after this kind of the vertex deprocessor is that we are basically interpolating all this kind of the vertex information for each of the pixel in the image space. So this is basically what we are going to discuss in the rest of the slides, which is basically the case that like when you have this kind of the three, for example, like the vertices for the triangle, for all the pixels included in each of the triangle, we're gonna interpolate the vertex information and then basically fill out the pixel information based on the interpolation. But in this process, what we are going to do is that we are basically also storing the depth information, the z-axis, the normalized z-axis information for each of the pixel. In terms of that, when you basically draw multiple the triangles in the images, we can see whether we need to overwrite the information in the images, or we need to just like keep the information in the images for now, and then just ignore some kind of the new triangle the information. So let's think about this simple the case. For example, like when you have this kind of the, I don't know whether this is the golden triangle or some green triangle, when you have this kind of the like one triangle, then we're gonna have like the projection of like these three vertices. And then we're gonna start to basically interpolate all these like the vertex information for the inside the pixel, which is like interpolating many things, as we can also discuss in the later these slides. But also we are interpolating the depth information, the z-axis information as well, which is basically giving the information about the distance from the image plane to the point in the 3D space. So actually, let's say like we do this some kind of the greenish the triangle, and then now we want to draw this gray triangle as well. So let's think about like this point. So we already have the information for this kind of a greenish the triangle with some kind of depth information, and then now we are also calculating the information based on the three vertices of this kind of the gray triangle, right? And then we're gonna also interpolate the depth information. So if the new depth information is basically, smaller than the depth information that we already calculated with the previous triangle, which means that the new triangle at this point in the new triangle is closer than the point that was drawn by the previous triangle, which means that we can overwrite the information, right? But let's think about this point. For this point, now we can see that the point over the gray triangle, the triangle, which basically the farther than the point over this kind of the greenish the triangle, which means that we should not overwrite the information. We just need to keep the information, right? So to determine whether we're gonna overwrite or not, based on the depth information, actually, that's the reason like basically why we need to basically not just projecting everything into the 2D plane, but actually we need to also have some kind of the preserve the the depth, the information in terms of like, that we are doing some kind of the depth test, just checking whether we need to overwrite or not. So that's basically what we also need to do in the rasterization step. in the next component. So that's the reason that we are basically having this kind of the 3D coordinates, which is called the normalized device coordinates. Yeah, so this is basically the coordinates that we are getting through the projection D matrix, which is still kind of the some 3D coordinates. Does it make sense? Yeah, and also kind of the thing is that now we can assume that everything in the Unicube is the only kind of the things that we are going to render into the image, which means that, okay, so one question in the Zoom chat. This is the only useful if we are rendering the same scene many times, right? Render the scene once, then we only need one depth test project onto a plane. We only render the scene once, then we only need one depth test project onto a plane is okay. One depth test projecting onto yeah, I couldn't get what exactly you mean, but basically even for the like rendering like one scene, there can be some kind of the multiple triangles, right? So we are not just like rendering a single the primitive, but there can be some kind of the multiple the primitives. Here the primitives basically mean the triangles, but that can be something else, right? So even when we basically render once the scene, there can be some kind of the multiple the primitives. And for like rendering the multiple primitives in the pixel level, we need to be able to see like what are the kind of the primitives that we're gonna render for each of the points. Then for that, basically we need to do some kind of the depth test. Then we need to preserve the Z information. So even when we render the scene once, if we have some multiple primitives, still we need to preserve some kind of the Z information and do some kind of the depth test. Does this answer the question, the Jung? Yeah. So that's kind of the process. And some kind of some hacky way that we can basically boost up the rendering the process is that now we can assume that everything in the Unicube is the only the information that we want to render into the images. So which means that we can ignore some kind of the triangles that are not present the inside of the cube. So for all the triangles that are outside of the cube, we can simply ignore them. So these are kind of the calling the process. So these are basically the calling, was kind of the occlusion calling. So basically we are ignoring all the triangles outside of the cube. And also we can define some kind of the front facing of each of the triangle. So for each of the triangle, we can see whether the triangle is visible from the like this side or the other this side, right? So we can think that the triangle is kind of having the two faces, like, and the only one face is kind of the visual face, and the other is basically not visible the face. So then basically we can check whether we are seeing the kind of the visible side of each of the triangle. And if we are not seeing the visible side of the triangle, then we can also ignore this kind of the faces. So these are also kind of the cases that we are doing some sort of the back face calling. And also for some of the triangles that are basically on the border of the cubes, that we can basically cut out these kind of triangles, as you can see here. Here, in a way that we can basically only consider this kind of some visible area of the triangles. So these are also the process that we call as the clipping. So these are kind of some kind of the techniques to basically speed up the rendering the process in the rest of the part. Okay, so this is basically the camera the projection step. And what we say about the divide by W, that we're gonna actually get into that later, is that now, what we can actually think about that is that, so we are not actually directly getting the normalized device the coordinates, but as I said, actually, the projection is actually the case that we are multiplying some kind of the 4x4 matrix, right? So simply just multiplying the 4x4 matrix actually can be considered as kind of the full D linear D transformation. And actually, it becomes the projective transformation when you divide the coordinates by the coordinates. So when you divide the final the output by the W coordinates, that it becomes the final the output of the coordinates in the projection. Actually, this becomes the normalized the device coordinates. And then before dividing by the W, this will be called clip coordinates. So we call these clip coordinates because like we can perform the clipping with the clip coordinates before we do this kind of the division by the W. But we're gonna basically separate these two. So we are having these like clip coordinates, which is just the output of the multiplying the 4x4 matrix. And once we do that, if we basically divide by W, if we then we're gonna get the coordinates that we're gonna see after the projection. So we are having the device, the normalized device, the coordinate system with this and X, Y, Z. And here basically this the G information is used for the depth test. So that's basically what we are going to do. Is this clear? So you're gonna see like why we separate these two, like why we have the clip coordinates and the normalized device coordinates. But the next step is basically simple. Like so once we get basically the normalized the device coordinates, then the z-axis information is used for the depth test. And then now the x and the y coordinates should be also mapped to the screen coordinates. So now everything what we have in the normalized the device the coordinates is that we are having everything in the range from the -1 to the +1, right? For each of the axes, we are having some coordinates from the -1 to the +1 the range for each x, y, z axis. But what we want to do is that at the end we want to map everything into the image coordinates. So when you say that the image has the size of the width of the W and the height of the H, then what we want to do is that we are mapping the upper left corner and the lower right corner into the here, 0 to 0, and these coordinates. So this is nothing but basically just like scaling the 2D the space in terms of that now we are mapping all the coordinates into the image coordinates, where basically we are having the left corner at the 0.0 and the right corner into the W point H. So it's like doing some kind of the non-uniform scaling in the 2D space in terms of like matching the image coordinates, while basically also preserving the G information with some kind for the depth test. So this is basically all the process that we are doing in the vertex processor. So we are having the model view transformation, which is converting the object coordinates into the camera coordinates, and the camera projection, which is basically multiplying the 4x4 matrix, mapping the camera coordinates into the clip coordinates, and then we divide by W so that we can get the final output of some kind of the coordinates for the projection, while preserving the G information for the depth test. And then we also apply some kind of the 2D non-uniform scaling in terms of also like matching the image the coordinate system with the image size. So that's the viewport transformation. And then we basically feed all this information into the the rasterizer. It is clear? Any question on this? No question. So what we can simply see is that like the transformation here, the model transformation was the basically 3D affine transformation, right? And also the last step also can be seen as kind of the part of the 2D affine transformation that we are applying some kind of 2D, the non-uniform descaling. And the camera projection was basically 4D linear transformation, just multiplying some kind of the 4x4 matrix, and it becomes the projective transformation when you basically divide by W. So this is basically sort of the only one step that is making non-affine transformation. So we're gonna get into this. Okay, so once we have basically applied this kind of the processing for the vertices, then now we are going to basically use this kind of the projected or the transformed vertex information to fill out each of the pixel information. So that's basically happening in the rasterizer. So the rasterization is actually kind of the process which is implemented in the hardware. So we are not, typically we do not implement this process, but we just use the pre-implemented function in the hardware to basically fill out the pixels using the kind of the vertex information, the projected the vertex information. So in the hardware, what is happening is that for all the pixels that are included by the 3D vertices in the project in the 2D plane, we are filling out all the pixel information by basically project interpolating the information. defined for all the three of the vertices. So that is automatically done in the OpenGL based framework. So you don't need to implement this part, but this is kind of some hardware implemented function in the typical graphics system. So what will be basically the information that we're going to interpolate? So there can be some kind of the multiple types of the information that we can define for each of the vertices. So that can be some color information or some texture coordinates. And obviously there should be the depth information as well. For the depth test, we also should be able to interpolate the depth information and some kind of alpha information like normal or whatever. Like there can be some multiple kind of the informations. So depending on the information that you are interpolating, you can also process them as you want. So that can be really any kind of arbitrary information that you want to interpolate and utilize in the later the fragment shader, fragment processor. So fragment here basically means the pixel. So once we basically interpolate the vertex information into each of the pixels, into the fragments, then you may want to also process that information to apply some kind of the textures or to apply some kind of lighting, whatever kind of things as you want. So that is also basically happening in the fragment shader. But here the question is that basically how we should basically interpolate the information for each of the pixel. So let's think about that we are having this kind of 3D vertex positions in the 2D space with the A, B, C, those kind of three vertices. And then for this pixel, P, we want to basically interpolate these 3D vertex information. So how can you do this? Well, I mean, these are basically applying the linear, interpolation twice, right? So we can think about that. We first basically drew a line like this. Can you see this, right? Yeah. Then based on the ratio like these two, the line segment, here and here, we can first interpolate the information of the vertex A and C, right? So that we get the new point M here. And then, based on the ratio like these two, you can apply the linear interpolation again, and then we get the final point P as well, right? So basically, we can compute the interpolation by applying the linear interpolation twice, right? But the interesting thing is that once you basically compute all the interpolation, actually that becomes the same as basically we are calculating some kind of the interpolation weights for each of these three vertices in this way. So what actually we can see is that the P actually, let's say like some kind of property of the P is like denoted as kind of for example, like V. And then we are having the information of the VA and the VB and the VC. So let's say these are some kind of the properties for each of the A, B, C, the vertices. Then we want to basically compute some kind of the interpolation weight. Like WA, like WB, like WC. So we basically want to do some this kind of the interpolation of the properties of the vertex A, B, and C. Then this weight for the interpolation actually can be computed based on the areas of the triangles. So if you divide this triangle into these three small pieces like this, the weight for this vertex can be computed as the area of like this triangle over the area of the entire triangle. And also the weight for the vertex B can be computed as the ratio of the area of the A2 and the entire triangle in the same way. So these are actually exactly the same computation actually as you do the linear interpolation twice by just drawing the line like this and just doing the linear interpolation twice. So you can actually check yourself. Now, how can you get this kind of the weights for those kind of the cases? So actually these weights for the interpolation, basically these weights for the interpolation to calculate the properties at the vertex P is called the barycentric coordinates. And you can easily actually verify that, how we can get this kind of the formulation of the weights by just like calculating the interpolation yourself. And also this is the case that the sum of the weights becomes the one, right? Because we are having this kind of formulation. Is this clear? Any question on this? So this sounds like, once we have, three vertices in the 2D plane, and if we basically specify any point here, then we can basically, for the pixel inside of like this triangle, we can basically calculate the various and the coordinates as kind of the weights for the interpolation. Then we can just like do some kind of the, some combinations, calculate the combinations of the vertex properties. So that will be kind of simple the process, right? So this sounds like what we can see in the rasterization, but it turns out that this is not exactly the step that we are doing the rasterization. So let's think about this case. So what happens if we interpolate the vertex properties using the weights calculated as the percentage coordinates? It sounds like the right way that we are doing some kind of interpolation, but it turns out that this is not the correct way that we should do. So let's think about this. Do you think that these two are the same? So there can be two cases. We can first interpolate the vertex properties in the 3D space and then project. And the other way around is that we first project the vertices, the first into 2D plane, and then interpolate in the 2D space. Are these two the same? So yeah, obviously the answer is no. So that's why we're going to discuss this. So these are basically the two cases. So basically what we want to do is the first case. So actually we want to do interpolate first and then project in this space. Then the competition becomes like more like trickier because like we don't know what's the kind of the interpolated point in the 3D space that will be projected into the each of the 2D pixel. So computation wise, this is like not easy. Like competition wise, this is like much simpler, right? But the thing is that if you project first and then interpolate in the 2D space, then this is what we're gonna get. So we are seeing there's some kind of a distortion in the output, in the rendered images. This is because of the fact that actually these two are not exactly the same. So if you project first and then interpolate, this is not the same that we are interpolating first and then projecting. So if we just like do the interpolation in the 2D space, then we will see this. So this is not we want to see, right? Actually, we want to see this. So here the question is that how we can properly compute all this kind of interpolation. So this is kind of the issue in the rasterization. So again, like what we want to do is that like I want to basically calculate the vertex property, some kind of the properties at this pixel, which is included by these like three vertices, by interpolating the properties of these three surrounding the vertices. So this is like what we want to do, right? So then what we can do is that from the projected the vertices in the 2D space, we can calculate the barycentric the coordinates as kind of the weights for the interpolation. So let's denote this kind of the barycentric coordinates as the alpha here. And this barycentric coordinates will be automatically calculated in the OpenGL rasterizer. So we don't need to even compute that. So that's good. But the problem is that if you interpolate the vertex properties using these weights, then it gives us the wrong outputs. So actually we should not use these weights. So if you basically want to match the results of the interpolation with the output of this, so let's say here, like so if we want to get these results on the left-hand side, that instead of the alpha here, what should be kind of the new interpolation device that we should use? So let's see that like we are having the this barycentric coordinates, which is basically defining the pixel point that we want to calculate the properties by the interpolation. But for the interpolation, actually, we should not directly use these weights to get the property outputs, right? So then what should be kind of the weights that we should use instead of this alpha, while we are basically specifying the position of the pixel using this alpha? So that's kind of the some big question in the rasterization. And for that, what we are going to briefly see is that let's briefly check out the affine combination. So affine combination is basically kind of the linear combination which is defined like this. Basically doing some kind of the combination, community combination like this, with only the constraint that the sum of the weights should be 1. So this is basically the affine, the combination. And the reason why we call this as kind of the affine combination is that this combination is invariant under any kind of the affine transformation. So whether you basically compute the combination of those things and then apply the affine the transformation, or whether you first apply the same the affine transformation into these the coordinates and then compute the combination, the output of these two are exactly the same. So that's kind of the like one important property that we need to remember. Okay, so for the any kind of the affine combination where the sum of the weights is 1, whether you first interpolate and then apply the transformation, or whether you first apply the transformation and compute the combination, the output should be exactly the same. So that's kind of the property of the affine combination without the proof. So let's basically keep this. Then what we can see is that all the interpolation that we are basically saying is basically the convex combination, which is basically a subset of the affine combination. So even we are not having the constraints that the sum of the weights is 1, but we also have some kind of constraints that the weights should be in the range of the 0 to 1, right? So for the Berg-centered the coordinates, we cannot have some kind of the negative weight and also the weights greater than 1, right? So this is kind of even the the case of the subset of the affine combination, which is called the convex combination. So which means that basically all the interpolation that we are calculating is a kind of a part of the affine combination, right? And also any kind of the linear transformation is also the affine transformation. So linear transformation is also the subset of the affine transformation that we are not having translation, right? And also one thing is that a sequence of the affine transformation is also affine transformation. So which means that if we are basically having the affine combination as the our interpolation, and if we only have the affine transformations, then actually we don't need to worry about those kind of things. We can just use the exactly the same the weights for the interpolation that we're gonna get the same the outputs. So if we get back to the vertex processor, what we can see is that we have some kind of the multiple the components here, right? For the model-based transformation and also for the projection until these points. So those are like the affine transformation and the 4D linear transformation. For those cases, it's okay to use the same weights. And also for this, the viewpoint transformation, this is another the 2D affine transformation. So this is also okay to use the same the interpolation weights. The only part that we are having some issue is this part. So if we start to divide the clip coordinates by the W value, then this is basically breaking everything. So this becomes a kind of the non-affine transformation, and this is the part that we should not use the same the interpolation device. So this is the only part that we need to handle for the proper the interpolation. Does this make sense? So here the question is that what we are going to do is that we calculated the interpolation, the weights, the alpha, using the normalized the device the coordinates. So we have the normalized device coordinates Q with the weights of the alpha. So this is kind of the kind of the way that we are specifying the pixel where we want to interpolate the properties, right? So then what the thing is that we want to basically interpolate the clip coordinates with the new weights better in a way that we get the same the results. So we want to basically match that these two be exactly the same with the interpolation of the here in a way that we choose the new interpolation the weights better here. So this is the case that we are basically interpolating the first and then kind of projecting instead of like just projecting first and then interpolating. So to match these two cases to be the same, what should be kind of the weights better that we need to pick that satisfies the affine combination here? So this is the last question for the 2D selector. So what we have seen is that we have seen that interpolating first and then projecting is different with the projecting first and then interpolating. And we specify the pixel that we want to interpolate all the things by the alpha, which is computed by projecting first and then interpolating. So based on the base and the coordinates, right? To get the same output with the interpolating first and then projecting, we need to recalculate the interpolation d ways, let's say, which is the beta. Then what should be kind of the beta here? That also satisfies the affine the combination. So since we are running out of time, so let's think about this. So you can think about this after the lecture. So this is a little bit kind of the tricky part in the rasterization. So actually the answer is basically this. So if we basically compute the beta like this, then this becomes the new kind of the interpolation the waste that also satisfies the another the affine the combination. So from this, what you can see is that for any kind of the vertex properties, now actually we need to interpolate the vertex properties not using the alpha, but with this beta, which is also defined based on the alpha and the W here. Actually, we're gonna get the results like this. So these are basically the output when you basically interpolate all the vertex properties using the new weight beta here. Then actually what we can see is that this is basically nothing but we are dividing this interpolation or interpolation of the vertex properties over the W using the weights of the alpha here and dividing this by the interpolation of the 1 over alpha, the 1 over the W, sorry, with the weights of the very sensitive coordinates. So which means that now if we can have the information of the V over the W and 1 over the W, then we can simply interpolate these two quantities using the interpolation the weights alpha, which is computed with the very sensitive coordinates. So the interpolation with alpha with the very sensitive coordinates will be automatically calculated using the rasterization the pipeline. So even you don't need to do that. The only thing that you need to do is that you just have this quantity V over the W and also the 1 over W. Just having this quantity to be ready to be interpolated with the rasterization the pipeline. And then you just divide the interpolation like this by the interpolation like this, 1 over the W. So this is kind of the exact setup in the rasterization. So if we see some details in the clip coordinates in the OpenGL pipeline, we're gonna have the XYZ the coordinates. So like this. So we're gonna have the XYZ coordinates of the clip coordinates and also the W parts of the clip coordinates and also some kind of the vertex properties that can be normal, color, depth, whatever kind of things. And then when you actually divide by W for this kind of the process, this is not only actually simply dividing by W. So we're gonna actually having some kind of the new coordinates divided by the W here. And then we just keep this. So this is just a kind of the extra information that we actually to compute some kind of the interpolation properly. So this is basically the information that we're gonna use for some kind of the to compute the interpolation with alpha using the base and the coordinates. And we just keep this extra information, 1 over the W. Then what we do is that we interpolate these two quantities like this using the rasterization the pipeline, and then we compute this over this in a way that we can calculate interpolation of the vertex properties properly. So this is kind of some sort of some details that are basically happening in the rasterization. So this is basically concluding the part of the rasterization. So we have the vertex processor and the rasterizer. And then in the fragment the processor, we're gonna also have some kind of the part that we are also further processing each of the pixel information by adding some kind of the texture, the image, of the kind of based on the interpolated the texture, the coordinates, and then we can also apply some kind of the lighting information as well, based on some kind of the interpolated the metrology properties as well. So we're gonna skip those kind of the details, but we're gonna get into some more details about the lighting in the rest of the course. Any questions on this? So this was kind of like very super quick summary of like what we are also discussing in the introduction to the course. So if you have also any questions and if you want to know more the details about this course, those kind of things, I also recommend you to check out the CS380 the course webpage. Also, you can find some kind of the materials there. And also feel free to ask some questions if you have any questions on those kind of things. And then next time, we're going to get into some more details about how we can also represent the 3D rotations in a different way using the quaternion. So these are kind of like reviewing some kind of the basics about the transformations and OpenGL pipeline. And after that, we're going to have some kind of the break on the next Wednesday. And then we're going to get into the details about the ray tracing the techniques. So in slide 47 or 48, shouldn't it be the affine subset linear? Yeah. So do you mind, so if for those questions that you posted on the Zoom chat, please post the same question in the Slack, then I will basically also follow up those things after the lecture. Yeah, please just copy the same thing into the Slack, whatever kind of the channel, and then I'll follow up those things. Yeah. Any other questions? So if you have any questions, please post the questions on the Slack, then I will also basically follow up the questions. And then I will see you next Monday. Okay. Thank you. Bye.